The title of this presentation is Entropy and Decay of the Optimal Value under Anchored Parallel Repetition, Normalization and Multiplayer Anchoring. To begin with a presentation overview of some results which we had mentioned in the second presentation, I wanted to again reiterate and draw the viewer's attention back to the fact that our main objective in multiplayer anchoring in determining how multiplayer anchoring differs from ordinary anchoring for various multiplayer settings is related to the fact that we have these three complexity related results, which we're going to demonstrate and further describe how they can be related to describe multiple or a decay of the optimal value of the game under multiplayer anchoring or under anchored parallel repetition. And pretty much how this has to relate is that we're having theorems 1, 2, and 3, these main results, which are all resulting from just basically probabilities and discrete probabilities, in fact, from several types of related conditions that I've been describing for the viewer, namely the fact that if we look at the bias and the optimal value in other types of related quantities, which we can define for the two-player setting, we can look at straightforward generalizations of these objects under the multiplayer setting. But furthermore, beyond that, if we're looking at the case in terms of dependency breaking variables and how this actually relates to removing correlations and observing decoherence in quantum states, which correspond to strategies that an arbitrary number of participants and players can use, that this can actually be of great use to actually determine what would actually be the types of parameters that would come into this big O notation, like through the complexity, through the three complexity related results that are provided on the slide. And in this presentation of this series, I was really going to describe and define more explicitly these components, which are coming into the fact that we see that we have in the first complexity related result for this system of expected values or expectations, that it's going to again relate to a lot of conditions which I was mentioning for the viewer at the beginning of the second presentation, the previous presentation of the series, in which pretty much I was describing how you can introduce some anchoring to either the questions or the answers which certain players respond to, and how this would actually relate to determining how to remove correlations and what would be the accompanying or the corresponding impact on the maximum winning probability for some game of interest. And we can see again in the second complexity related result, I really drew the attention of the viewer from previous remarks to POVMs, which are positive operator valued measurements. That's what it stands for, that acronym. And how this actually relates is just basically allowing one to take a trace of a tensor product representation of operators and being able to define that as a probability. So it really shouldn't come then as much of a surprise that if we're starting out with expectations which are ultimately taken with respect to probability measures in the first complexity related result, that in the second complexity related result with POVMs, the positive operator value measurement system, that we're going to replace some of the components, some of the probabilities with positive operator valued measurements, and hence this would allow us to make some type of connection between the big O function, the big O notation, and the computational complexity that would be used or be needed or requisite or necessary to bound the expectation values which are appearing in the POVM system, which have components which are dependent upon positive operator valued measurements. And finally, for the third item, we're going to also be able to make an equivalence between the POVM system or the system of expected values, which include dependencies on POVMs, which is given in the second result, and how that would actually be able to relate to a third and final system of expected values, a third probabilistic system, if you'd like, which can be upper bounded with Pinskers inequality, which is a very typical type of inequality in quantum information theory, which I defined from some of the tools that we can use in quantum information theory from the previous slide, which is really resulting from the fact that the L1 norm between two quantum states around sigma can be upper bounded in terms of the summation of the relative entropy. And the relative entropy, as one shouldn't be surprised. It comes into play because the relative entropy and the relative min entropy have various relations with the mutual information entropy, which is another type of entropy which I discussed, which I recently, 4 or 5 weeks ago in my previous preprint to the archive that I put out. I examined the mutual connections between the mutual information and the conditional Shannon entropy for the transmission of quantum information or of classical information across a quantum channel. And now I'm just going to further describe some, beside these three complexity related results, a few of the objects which we had introduced in the previous presentation, just to reiterate things very briefly again. And this is just given by the fact that we can define anchoring probabilities, which is given by these sequence of probabilities corresponding to each one of the players. So the little q1, little q2, up to little q of big N, they're denoting the questions which are being distributed to each one of the players. And the support of each one of these probability measures that we're going to define, that we're going to use to define anchoring through this LaTeX bot symbol, the bot symbol, is going to denote that we're interested when we're setting certain questions to an anchoring with some positive probability, that basically this is going to have the effect of removing correlations, but simultaneously, hopefully, in the most optimistic case, not significantly or drastically impacting the probability that two players or a collective or a group of arbitrary number of players and participants can win some game of interest that's determined from the referee's scoring predicate. And so we see that each one of these D is equal to script A, all the way up to script of A of N is conditioning upon the result from the answer of each one of these players. And M is indicating that we're performing some type of measurement to actually determine from some type of quantum state that a player uses for participating in the game, what would be the expected outcome of different types of quantum strategies in the sense of optimality or near or approximate optimality. And again, the viewer can recall that in the previous presentation of the series, I described how one can define these probabilities depending upon whether the question is anchored or not. Namely, the fact is we can see from the piecewise defined function for the first probability measure under anchoring for little q sub 1 for the question distributed to the first player from the referee's probability distribution, that we have p of script q sub 1 is a function of the question, an instance of all of the questions that can be distributed to the first player from the referee's probability distribution normalized in 1 minus eta, where this eta parameter is given by a half of the anchoring probability, so alpha over 2. And again, the anchoring probability is just the probability that certain responses and questions that are distributed to the player can be set to some type of element from the anchored set, which is removing quantum correlations and hence removing the amount of entangled quantum information that this player can share with all other participants in this multiplayer game theoretic setting that we've been describing. And furthermore, we can see that if we do set the question little q sub 1 that's distributed to the first player, that the referee from the referee's probability distribution that the referee wants the player to provide an answer to for determining whether it satisfies some scoring predicate, this is equal to alpha minus eta over 1 minus eta if and only if we actually set this question equal to to be anchored. And we can see that in a straightforward type of way, depending upon whether any one of the remaining questions which are distributed to the players in the game are anchored or not, we can define and introduce similar types of expressions using alpha and eta, namely the eta parameter, which is relating to 1/2 of the anchoring probability alpha over 2, and how this can allow us to introduce anchoring probability measures. And so the anchoring probability measure corresponds to, for each player, is defined as follows. Recall that on the other hand, if we can also introduce ways to observe decoherence in a quantum system, depending upon if any one of the answers is anchored from some type of player's response, which is identically equivalent to the probability supported over the questions script q sub 1 for all of the questions which can be distributed to the first player from the referee's probability distribution. That player 1 responds with an answer from the anchored set is identically equal to alpha, and we can introduce this uniformity in the anchoring parameter for all of the other questions and responses which are distributed and answered from the players in this multiplayer setting uh, up to big N number of players. And the computations for upper bounding the POVM, the positive operator value measurement system, are dependent upon the relative and the relative min entropies, like I had been describing. Namely, if we adopt the notation for the probability measure from Jane and Kundu's paper that we've been describing, because they have been providing some type of generalization in terms of the decay of the optimal value under anchored parallel repetition, it just basically amounts to computing an expected value and expectation of the relative min entropy of state 1 with state 2, which can be identically expressed in terms of this S infinity function, which is the relative min entropy between state 1 and state 2, where the expectation is still taken with respect to the same probability measure as what's given in the previous line above it. And the relative min entropy is defined in terms of given two quantum states rho and sigma, S infinity of the relative min entropy between rho and sigma is the minimum of lambda such that rho is less than or equal to 2 to the lambda times sigma. And in the two-player setting, state 1 and state 2 are defined through the following traces. Oh yeah, I'm sorry, just really briefly, apologies. There's a little typo here. I corrected it in the paper, but it should just be Alice's unitary for the first state. So basically, we're defining traces of these tensor product representations, which is corresponding to the multiplication of Alice's unitary with some tensor product of theta and sigma, where theta and sigma correspond to two quantum states that we're looking at some instance of that we're going to look at and consider some instance of dependency breaking. And DG is the dependency breaking notation, which is introduced in Jane and Kundu's paper. And also, we're hitting this tensor product representation with the complex conjugate of Alice's unitary. And similarly, for state 2, we can define a similar trace in terms of Bob's unitary instead of Alice's unitary, and also replacing theta and sigma with theta prime and sigma prime, respectively. And as the viewer will recall from the last presentation, I was devoting quite a bit of attention and time towards the fact that one would like to generalize computations with entropy for multiplayer game theoretic settings. And pretty much I felt that it was appropriate and very accessible at that to mention this type of connection between computations with the entropy, pretty much from the two-player case out of the box, so to speak, and how this would relate to multiplayer game theoretic settings, because it's actually one part of, one component of the argument that's actually pretty straightforward, and actually building up and further adding intuition and knowledge to the uses of the relative min entropy for these computations, and how this relates to upper bound in the POVM system, and also how this relates to the other two remaining complexity theoretic results, then allows us to pick away and chip away at the types of computations that someone would need to obtain those three desired complexity related theoretic results, and how they relate, again, like I've been describing for the viewer, to the decay of the optimal value under anchored parallel repetition. And so, as one will recall, we were describing that for the multiplayer setting, one argues that the expectation with respect to the probability measure supported over big N number of questions, which are distributed from the referee's probability distribution to each one of the big N capital players in this multiplayer game that we've been describing, is given by the expectation of the relative entropy of the multiplayer state 1 with multiplayer state 2, where again, one can straightforwardly define multiplayer states in the same type of way that I'd introduced it in the previous slide for Alice and Bob, just namely taking some types of unitaries which correspond to each players and taking a tensor product representation of quantum states and then performing the complex conjugation action of the unitary, namely to the left of this tensor product of states, which is given it as the middle intermediate term of the trace, we're just multiplying by the player unitaries, whereas on the remaining term, we're multiplying by the Hermitian complex conjugate of these unitaries, and we're taking the trace of this tensor product representation. And how this actually relates to, again, the relative entropy and the relative min entropy, because this first expectation, which is given in the first line of this slide here, it's identically equal to just S, which is just the relative entropy we're letting the parameter before we're letting the subscript in the entropy approach infinity, and before we're getting the relative min entropy. And then finally, because we know that the relative min entropy upper bounds the relative entropy, the expectation of S of the multiplayer state one of the entropy between the multiplayer state one and the multiplayer state two is upper bounded by instead the expected value of the relative min entropy, the S infinity entropy of multiplayer state one with multiplayer state two for these types of states which I've been describing. Again, where we can endow and give each one of the participants in the capital N players and agents in this multiplayer game theoretic setting their own unitaries, and they can make use of these unitaries for being able to perform some type of complex conjugation action. And this type of action, or it appears all throughout all throughout quantum information theory and quantum physics, because we're looking at some type of trace of this tensor product representation corresponding to these states, which are appearing as parameters in terms of the relative min entropy and the relative entropy. And so now I wanted to provide an overview for the third presentation of this series. We've been spending a little bit of time describing what types of objects we manipulated and how this relates to entropy and multiplayer game theoretic settings. And so now we're going to be describing and adding on some further detail to these topics of discussion. And so this is allowing us to basically continue describing how the three main results of a complexity theoretic interpretation are obtained. And then we're going to introduce along these lines additional properties of probability distributions, various forms of rates of decay for the optimal value under ordinary and anchored parallel repetition. And this will allow us to establish more comparisons with expanded and multiplayer game theoretic settings. And altogether, this is going to allow us to distinguish and further describe, like I've been mentioning, what is the significance of the ratio which is appearing in the big O notation, namely one will recall from those three complexity theoretic results, which I've pretty much been mentioning and describing at each one of the three presentations of the series so far, that it's dependent upon a delta multiplayer parameter normalized by alpha multiplayer, namely some threshold, some multiplayer threshold delta, which is normalized in the multiplayer anchoring probability. So I'm going to further be describing and adding on some further color and light on these objects. And so I wanted to provide a couple of conditions which are underlying ultimately the probability measures. So this is just basically relating to describing more aspects, discrete probabilistic aspects and foundations, and how this relates to games that players use that we have been ultimately mentioning from the last presentation of the series, and that we began first discussing then. So it's just pretty much saying that the probability can be upper bounded with this type of expression. So namely, if we looked at script q sub 1 up to script q sub m, which again, like we've been describing, is the set of questions that can be distributed to each one of the arbitrary number of players from the referee's probability distribution. The L1 norm can be upper bounded by, as in this first case, for when the support of these two probability measures is taken in terms of script q sub 1 and script q sub 2, it can be upper bounded with 2 times the probability of the joint support of q sub 1 and script q sub 1 and script q sub 2 simultaneously, given the fact that script q sub 1 is not equal to script q sub 2. And one can build up straightforwardly this type of similar analogy for other types of probability measures, namely that if we want to, instead of just upper bounding the L1 norm or just the standard absolute value distance of the probability measure of script q sub 1 minus the probability measure of script q sub 2, we can instead look at the product of the probabilities, namely the probability of script q sub 1 and the probability of script q prime sub 1 minus the probability of script q, or the probability of script q prime sub 2, which can also be just further upper bounded in an obvious type of way in terms of two times the probability with these with the product of these four question sets, namely the two unprimed question sets and the two primed question sets, such that none of the question sets are equal to each other. And this is just one type of information or one type of property of discrete probability measures and discrete probability in general, and how this relates to information processing, and how it's actually relating to the fact that these are the types of probability measures which we usually like to consider or that we like to study when we're talking about information processing, because we're pretty much looking at, like how we've been describing, what is the probability for players to be able to achieve certain outcomes, or for a collective of players or participants or agents to achieve some type of winning formula or to win some game, even if or just basically given the constraint that we look at anchoring their questions or their answers for these players in isolation while leaving the correlations from quantum strategies and quantum states that players use in the remaining of the system unchanged. In the second condition, and obviously this isn't a collection or a rundown of all of the conditions for probability. I'm just for discrete probability measures that I've described in this upcoming paper. It's just a couple of conditions that I thought were helpful just to continue adding some more detail. But the second condition on probability distribution supported over the questions distributed to each player is the following. Namely, in a similar way that we had described in the previous slide, that the probability measure for script q sub 1 minus script q sub 2 can be upper bounded with two times the probability, where the support of this probability measure is some joint quantity, namely some quantity that's taken from a product of script q sub 1 and script q sub 2 upon conditioned upon the fact, or conditionally, or basically which holds, given the fact that script q sub 1 is not equal to script q sub 2, we can form a chain or a sequence of upper bounds of probability measures, such that we're starting from this probability measure, which is given in the lowermost in the lowest bound, and then we can actually be able to formulate some type of upper bound, which is given by different instances, as we see here, the probability measure of script q sub 1, the same probability measure, but with a different support, q sub 1 prime, all the way up to q1 with an arbitrary number of primes, minus the probability of q sub 2 prime, up to an arbitrary number of primes for the questions that are distributed to the second player from the referee's probability distribution. And I really wanted to also begin describing more of the connections which are related to what is the main overall thrust of the complexity related theoretic results. And this is just basically relating to the fact that the rate of decay of the optimal value for two-player anchored parallel repetition is very important to consider. And that's actually one of the main results of the complexity theoretic types of arguments that have been previously executed for two-player settings. And so we're just going to spend a little bit of time describing a couple of the quantities which are introduced in the optimal value under anchored parallel repetition in the two-player setting. And so, namely, that's given by the fact that we're looking at generalizations of a previous item for expressions of optimal values under anchoring. And just basically following the authors of these three references that I have in my paper, which again are the types of references that I was describing in the previous presentation due to Bavarian, Vidic, and Ewan. The authors of 30, Jain and Kundu, which have also been describing their reference, argue that a generalization of anchored parallel repetition of the optimal value satisfies this quantity. Quantities of this type of form for the anchored parallel repetition, given one-sided anchoring, are actually pretty common throughout the literature, and it's pretty interesting to determine, say, how would the function, this omega function, which is in which we're raising these probabilities to before anchoring to determine some estimate for anchored parallel repetition differ. And pretty much what the formula is that we're taking 1 minus an optimal value, But within the caveat is that within these large parentheses, we're raising this one minus the quantum optimal value to the fifth power. So basically, there have been several different types of works within the literature which have been determining how, say, maybe again, this value of omega as well as this value of the power 5 would actually relate to and be dependent upon instances of parallel repetition and anchoring. And the overall power given the function omega that we're raising this whole expression to is given as being dependent upon the logarithm of the product of the set of answers from the first player, Alice, and the set of answers from the second player, script B, corresponding to Bob's answers, as well as K being the parameter, which is the number of parallel repetitions, which is strictly positive. And an alternative way of expressing dependency breaking variables can be obtained from the following form. We can also be able to express the function omega, which is the parameter in the function, which we're raising this one minus the optimal value to in terms of in order to get some type of estimate for the optimal value under anchored parallel repetition in terms of just being identically expressed as a union of all functions, little a and little b, where little a and little b are respectively different instances of answers that Alice and Bob can provide for questions in response to questions drawn from the referee's probability distribution, which in itself is given by the set of functions which is dependent upon script A and script B. And the probability of sampling dependency breaking variables for expanded games, again, is coming of interest because, as I described and motivated for the viewer in the previous presentation of the series, pretty much we can look to expanded games as a very helpful two-player game theoretic setting for being able to expand into multiplayer game theoretic settings or maybe even other two-player game theoretic settings. Because I mean, after all, that's what I had done in one of my previous first works, more in the quantum information processing and quantum information theory side of things that I described for the viewer, in which pretty much I looked at XOR star and FFL games, and I was establishing connections between two-player game theoretic settings through the XOR star and FFL games, and how that actually related to XOR and CHSH of N games, and how pretty much those types of games are very prominently, they've been studied and they've been of great intense and great focus for researchers for quantum information for basically being able to determine model systems of entanglement, EPR pairs and Bell states, and just basically being able to generalize models of entanglement from these simpler, lower dimensional two-player game theoretic settings. And so again, that's just to reiterate that the decay of the winning probability under parallel repetition with regards or with one-sided or with, I think, sorry, this should just be anchoring. So basically, one-sided or anchoring along the lines of the previously mentioned condition stipulates that we can just look to, or sorry, it should be one-sided anchoring. Apologies, because we're pretty much still looking at the probability of sampling the expanded set of the set of expanded multiplayer dependency breaking variables and how this relates to the conditioning that we're winning across all coordinates, in addition to the fact that we're setting the question that's distributed to the first player boldface x sub I to be identically equal to some instance little x. And so basically this is given by approximately the conditional probability that we're sampling the expanded dependency breaking set, given also that the additional constraint in the conditioning of this probability that boldface y sub I, namely the question that's distributed to the second player from the referee's probability distribution, is identically equal to y, as well as given by the fact that this probability, again, like from the type of statistical condition in the statistical sense with respect to the absolute value little L1 norm, can be approximately given by the conditional probability upon just boldface y instead of boldface x sub I and boldface y simultaneously. And this is just to reiterate that because we want to establish some type of rate of decay on the two-player optimal value, the requirements for the one-sided anchoring imply for non-local two-player games as suffices to consider an expression of the following form, namely that we're going to obtain this type of expression, and this is going to be related to the complexity related results, which are ultimately relying upon the mutual information entropy, the relative entropy, and the relative min entropy. And parallel repetition of entangled games uh, have also been considered by Ewan in one of his works individually, in which he obtained some rate of decay. And his rate of decay from one of his papers is actually very similar, and it's actually demonstrating how the factors and the contributions from different players can actually depend upon, similar types of parameters which have come into play, which I'm going to describe for the exponential rate of decay that was obtained for anchored parallel repetition in the paper due to Bavarian, Vidic, and Ewan, namely given by the fact that Ewan in one of his papers, which I believe if I remember correctly was a conference proceeding, he looked at the value star, so namely the quantum value of the entangled game G entangled, which is being upper bounded less than or equal to some universal strictly positive constant C sub G, depending upon the game G, as well as the cardinality of the answers provided by Alice, as well as the sorry, I forgot the absolute value bar there, but the absolute value of the log of n normalized in epsilon to the 17, which is another strictly positive parameter, and little n to the 1/4, which is the number of parallel repetition operations. So we can see that typically speaking, when we're looking at the rate of decay of the optimum value, it will depend upon some type of quantity, which is allowing us to consider, namely, what is the log of the product, or, just basically some quantification of the product of the number of answers that each one of the players can respond with, the number of parallel repetitions, some universal constant depending upon the game, as well as maybe additional logarithmic or exponential factors, which are encapsulating all these factors together. And Ewan, in that same paper, that conference proceeding that I described, in which he obtained the result from the previous slide, he then was able to conclude that the value of the entangled game under parallel repetition for little n rounds, like how we said, this was the little n which was appearing in the normalization of this less than or equal to upper bound for the entangled value, for the quantum entangled value, or the quantum value of the entangled game, he was able to obtain some type of expression of this form. And one can see that in many types of ways. This is a specific instance of the type of optimal value that I'd given, or it has a lot of similarities with the type of optimal value which was obtained by Jane and Kundu. And I don't know exactly which paper was first. I think probably Ewan's paper was first, but still, nevertheless, we can see in terms of the differences, namely the fact that this the power that we're raising this big parentheses to is instead depending upon, again, this universal constant C sub G entangled, which is just identically equal to C sub G. And then this is just equal to this is also being multiplied by little n, which is the number of parallel repetitions of the entangled game, as well as this factor of 1 minus the value of the entangled game being raised to the third power. So we can see that that was why it was really helpful to consider a more general type of expression for the that was provided by Jane and Kundu, because it very clearly illustrates how different instances of parallel repetition can be studied for different multiplayer game theoretic settings, or even two-player game theoretic settings, and basically how at the end of the day you can relate and look at these two, or these basically these types of interpretations as being related to each other in terms of removing correlations from quantum systems like we've been describing. And the two-player thresholds for the complexity related theoretic results are given by the fact that, again, we're looking at upon several factors that come into play, namely, again, like we've been saying, the size of the cardinality of the answers provided by Alice and Bob for the two-player setting, as well as the ratios K, where K sorry for a little bit of the abuse of notation, but apologies for that. But K actually in this case, it's denoting the rounds of parallel repetition. It's just it's kind of confusing because throughout the literature, some people always denote it with little k or little n, but in this paper, little k was denoting the rounds of parallel repetition. And this is given by being normalized by the log, like I had been mentioning, the log of the product of the answer sets respectively provided by Alice and Bob. Also, is given by the fact that C, which is coming into play as the anchoring probability, is given by C squared times K times the number of parallel repetitions normalized by the same logarithmic quantity, namely proportional to the product of the answers provided by each one of the players. And the components to the multiplayer thresholds in the three main complexity theoretic results can be straightforwardly obtained from these types of quantities. Namely, if we're taking big K to be the number of parallel repetitions, we can look at the logarithm of the product of script A sub I, where script A sub I, this product over script A sub I is corresponding to the answers that are provided by each one of the questions for the players, as well as given by the fact that we can look at the remaining normalization, which is coming into play in the multiplayer game theoretic threshold in terms of the anchoring probability raised to the capital N power, namely raised to the capital to the number of players and participants in this multiplayer game theoretic setting, multiplied by the number of parallel repetitions, which is again normalized by the log of the product of the cardinalities of each one of the answers provided for the players when they respond to questions drawn from the referee's probability distribution. And so typically within quantum information theory and quantum game theory, the way of defining the optimal values defined is introduced in terms of omega being identically equal to a supremum overall strategies where the winning probability is dependent upon all the possible strategies that a player can make use of to his or her maximum benefit for winning. But one can also define, which is also helpful, the optimal value of the game with an infimum instead of a supremum over all possible strategies. So namely, the worst case winning probability, omega star sub WC, which is corresponding to an infimum over quantum strategies of the winning probability. And this again comes into play because we've been describing basically different types of ways to be able to introduce quantifications of the decay of the optimal value. And this is even given by the fact that if the viewer recalls the types of expressions which I have been giving as an overview for the optimal value and how this relates to the complexity theoretic related results for the multiplayer settings and the decay of the optimal value that I'm interested in describing in obtaining in my upcoming paper and project, it's really given by the fact that the quantum optimal value omega star of G of K, namely little k rounds parallel repetition, where k is again like usual taken to be strictly positive, it's upper bounded by some 1 minus epsilon parameter, namely 1 minus some sufficiently small parameter. So basically this epsilon parameter is taking the place of the 1 minus optimal value. But this is also taking the place of this omega factor, which was appearing in terms of omega, which was dependent upon the cardinality of script A and the cardinality of script B, instead being dependent upon C squared, namely the square of the anchoring probability, this strictly positive epsilon parameter raised to the fourth, as well as the number of parallel repetitions K normalized by the logarithm of the product of the answers from each one of the players. And sorry, there's a parentheses I have to close out. I always catch I always catch little typos in these presentations, unfortunately, but that's why I do them. And so the game theoretic thresholds that Jane and Kundu use, they're really related to these types of results. And I felt that it was really interesting to describe the results because it's demonstrating one type of way that we can further gain a handle in terms of what types of computations that we not only need to perform with the relative min entropy, but also how this relates to the parameters which are appearing in the rate of decay for the optimal value. And this is just given by the fact, as it shouldn't be surprised, it's very similar to these types of parameters which is appearing in this expression for the previous slide. Namely, given the fact that we're looking at some square of the anchoring probability in the fourth power of some sufficiently small parameter epsilon, but just obviously the non-trivial part is this normalization that they're using as a prefactor, not only in this first expression, but also in the second expression as a per factor to the logarithm of the product of the question sets from each one of the players. So pretty much, obviously I'm not here to explain or justify why they use this type of normalization, but it's just basically saying that one type of way in terms of being able to obtain some type of related complexity theoretic result, like what Bavarian, Vidic, and Ewan originally obtained in their work from those three results, namely upper bounding the system of expected values, upper bounding the system of POVMs, and then also finally upper bounding the system of expectation values with Pinsker's inequality from the tools in quantum information theory that we had described in the last presentation in the series, that's pretty much even related to adjusting these types of thresholds. And again, as we have been describing, adjusting the logarithm of the product of the answers that each one of the players can provide in response to the questions drawn from the referee's probability distribution. In the multiplayer game, theoretic settings pretty much take this form. So again, it shouldn't come as a surprise that we're taking some capital N, um, some capital N version of the anchoring probability, and we're also taking some larger power of also the strictly small or strictly positive, sufficiently small parameter epsilon, but normalizing maybe by some other type of constant, which would allow us to obtain some type of similar complexity related theoretic result if we were looking in terms of, following more directly the argument due to Jane and Kundu. And obviously, whenever we're talking about quantum information theory or even quantum algorithms, like I've discussed in some of my other presentations a long time ago, you can look at unitaries, namely unitaries corresponding to each one of the players' script u sub 1 up to script u sub n. And now I'm going to be describing more aspects of the system of expected values, which are given without normalization. And this is actually relating to script of E, which is given by the system of expectation values, which are taken with respect to each one of the unitaries. So basically what we want to look at is look at some instance of dependency breaking conditionally upon the fact that we're winning across all of the coordinates, which is given in terms of all these expected values in these systems as the outer expectation, whereas in the inner expectation, we're looking at expectation of script q sub 1, expectation of script q sub 2, up to expectation script q sub n. And this is actually relating to the actual quantities and the quantum states, which we're going to take the expectation of, which we can see is given in the first slide as being the tensor product of the first unitary with n minus 1 copies of the identity minus the identity minus 1, which is acted upon some quantum strategy and some quantum state, and being able to just basically permute and move forward the position in which the unitary appears in this tensor product for all the other remaining expectations that appear in the system. And I wanted to introduce this expectation and this expected value first because this is pretty much demonstrating how one can make use of different aspects of, looking at various generalizations of this system of expected values, because this is ultimately the beginning quantity that we want to look at in terms of upper bounded for the complexity related theoretic results. And so relatedly, the dependency breaking states over the number of players is given by the following decomposition. We're looking at kep psi, which is identically being equal to dependency breaking amongst the first k players, where we're ranging k to be between 1 and big N inclusive, and we're looking at psi k. So again, this is just relating to the fact that, like I mentioned in the first presentation and the second presentation of the series, we're looking at providing some instance of dependency breaking variables amongst different rounds of parallel repetition and determining what would be the impact on the winning probability through these types of various quantifications of decay of the winning probability that I've been providing. And then the system of expected values, like I gave 2 slides ago, it can be related to some similar system of expected values, but instead twiddle a script E, in which the twiddle is normalizing or signifying that we're introducing some type of normalization for the quantum states, namely the fact that we're looking at some twiddle of kep psi for each one of these values, while we're keeping the outermost expectation, namely the instance of dependency breaking big R sub minus I at position away from position I, as well as conditionally upon the fact that we win across all coordinates while looking at the support of these expected values being the same. And we're still making use of all of these unitary script u sub 1, script u sub 2, up to script u sub capital of n. And the normalization of the quantum strategies, which is appearing in the normalization of the expected values, is given by the following fact, namely the fact that we can look at twiddle of kep psi, which is identically being equal to kep psi normalized by itself, which is proportional to kep psi. So basically, this type of normalization, again, is why I mention it in terms of the title of this presentation, because it's demonstrating not only how one can make use of expected values, but also be able to describe generalizations through normalization or other types of normalizing factors, which are coming into play with the complexity related theoretic computations for obtaining those three main results, which have some bearing and some significance on the decay of the optimal value under anchored parallel repetition. And so again, this is just really reiterating again, I just really wanted to keep on focusing and emphasizing this type of point that now what this is really coming into is all these game theoretic interpretations are coming into play that we're just writing out some system of expected values and adjusting where appropriate the support of each one of these expected values and hence the support of the underlying probability measure and how this actually results in just basically looking at the norm of some quantum state, of some tensor product representation or some tensor product operators which are acting on some quantum state. And so two properties mentioned in the previous presentation, which I'd kind of at the moment I swept a little under the rug, but I mentioned would be great to come back to, is that we're going to describe sampleability and the usefulness properties. The first property, sampleability, in addition and in tandem with usefulness, it's coming into play because these are properties that players can use basically to ensure that some certain rate of decay of the optimal value is obtained in spite of the fact that they're making use of dependency breaking variables. So basically, the first property asserts the existence of some state big of theta or big theta, independent of the questions that are distributed to each one of the n players from the referee's probability distribution, as well as another state little theta, which is dependent upon these questions, so that the unitary or the tensor product of the unitaries for the n players applied to big theta minus little theta in the L1 sense or the L1 norm is approximately zero. And also, second, the usefulness condition is asserting that each player or each participant or each player in the multiplayer quantum game can perform a measurement, respectively denoted M1 up to M sub n, namely script n sub 1 up to script n sub big N, such that the measurement of little theta that was given from the previous item minus the probability of this conditional probability is approximately zero, and how this type of approximation with regards to this norm holds for all of the measurements up to script m sub big N. So basically, this is again demonstrating how we have been describing how we had wanted to really establish a connection between positive operator value measurements and tensor product representations of operators and traces of tensor product representations. And this is definitely encoding part of that correspondence in part of those remarks, which I've been mentioning in previous presentations, namely the fact that if we look at the support of the probability measure over the question sets q sub 1 up to q sub n, conditionally upon the fact that we're distributing questions little q sub 1 and little q sub n to the big N players, conditionally also upon the fact that they win across all coordinates, we can subtract that from the measurement operation applied to this theta quantum state. And the system of expected values under anchoring can even take a more generalized type of form because one can recall that I was giving expected values for twiddle of script E, but we can also look at the system of expectations or the system of expected values for twiddle script E of bot, namely the anchored system of expected values. And this is again given by the fact that it shouldn't come as a surprise at all to the viewer that we're keeping the support of the two expectation values the same. But what we also have to keep in mind is that is that what we're changing is that we're changing normalization, namely the fact that instead of just having the quantum state instead of having one quantum state for each expected value, we're actually having two quantum states, namely twiddle of this psi term minus twiddle of another psi term, where each one of the psi terms differs in the sense that we're looking at whether there's a bot, namely whether there's anchoring for the first question, or there's an anchoring for the second question, or there's an anchoring for the big nth question, and so on and so forth. So there just are basically many types of combinatorial interpretations and possibilities which are apparent through this system of expected values that one introduces for this system of expected values under anchoring, and how that basically relates to changing the anchoring amongst different questions and hence amongst the possible responses and answers that players that even an arbitrary number of players in the multiplayer game theoretic setting can provide in response to questions drawn from the referee's probability distribution. And so again, this is just given by the fact, as one shouldn't be surprised, is that each one of these twiddle psi states is given by the state normalized by itself. And this is just basically providing all of the notation just to further clarify the twiddle the normalized states which were provided for the normalized system under anchoring in this slide. And so again, we can even introduce another type of variant of this type of system under normalization by introducing a perfactor for the normalized state that's given in the second position. Namely, we're looking at some type of normalization of psi of Q1 up to Qn, which is given here, normalized by psi of anchoring amongst all of the questions for the big N players. And then we can basically introduce in the second item, the second expectation within the system of expected values right below it. Instead, an anchoring on the first question while leaving the remaining n minus 1 questions, namely Qn, Q2 up to Q big N the same, while still normalizing by anchoring amongst all the questions. And again, this further adds to the combinatorial interpretation of what we can actually use and introduce in terms of being able to generalize system of expected values with either normalizations in terms of these perfactors, which I've given here, in terms of these ratios of these psi state of these kept psi states, as well as the twiddle of kept psi states, which are allowing us to be able to perform ultimately computations with the relative min entropy so that we can be able to conclude and deduce some desired type of decay of the optimal value. And so the generalized form of the system is just given by this form, namely that we're looking again at that twiddle of script E is given by just basically this tensor product representation of operators, this tensor product of operators from each one of the unitaries from all of the players, minus the normalization, which is acting on some kept psi of or a twiddle of kept psi state. So namely some normalization of the kept psi state. In the system of expected values with normalization, with normalized quantum states, again, we abbreviate just in the paper, I abbreviate it with gamma factors, big gamma factors. So gamma sub 1 up to gamma sub n. And then basically when we're looking to perform anchoring amongst several questions amongst the big N number of players simultaneously, one can take a product of these gamma factors, which is given in terms of the last expectation value, which is given in the system, in which we're looking at minus a product of these gamma sub I factors, as gamma varies between 1 and big N inclusive. And so the multiplayer normalization, which we're describing in these gamma factors, these big gamma sub I factors, which are appearing in the previous slide, is identically being equal to the norm of the indicator that the first ith questions are anchored, which is multiplied by the kept psi state, namely the quantum state corresponding to some instance little r of minus I of dependency breaking, as well as anchoring the first I questions and leaving the I plus 1 to the nth question, to the capital Nth questions unchanged, so unanchored. But then this is given by the normalization of the fact that we're normalizing by the indicator function, by the norm, that the indicator function that all the questions are anchored is multiplied by the kept psi of r to the minus 1, where all of the questions are anchored. So again, this is just really reinforcing that type of interpretation which I've been providing for the viewer, namely the fact that we can look at various ways to construct schemes, I guess one could say, are different ways of anchoring some questions or some fixed subset of questions simultaneously or maybe at once, and how this would relate to the system of expected values and the corresponding tensor product of operators that we're going to be looking at within system of expected values. And the result due to Bavarian, Vidic, and Ewan for three-player game theoretic settings is given by the following. So just basically for all r sub minus I, x, and y, namely questions distributed to the players Alice and Bob from the referee's probability distribution, there exists dependency breaking unitaries, which are given by u sub r minus I sub x acting on E sub a, where E sub a are just some registers of a quantum circuit that I've provided as a diagram in my upcoming paper, along with the dependency breaking unitary v sub r minus I of y and v sub r minus I of xi acting on E sub b, namely another subset or another set of quantum registers, such that with probability at least 1 minus big O of delta of 1 over 16 for delta to take him to be sufficiently small over the choice of uniformly randomly chosen coordinates I with between 1 up to n, which are outside of the set of all coordinates big C, they basically provide some type of upper bound and some complexity related theoretic result, which is again really relating to the type of generalized system which I've been formulating. Namely, one can establish and immediately observe several types of similarities between the system of expected values that they provided in their results and how it relates to and informs the type of system of expected values in various generalizations of system of expected values, which I was trying to provide for the viewer, namely given the fact that the outermost expectation in each one of these quantities, it's given in terms of the expected value of r to the minus sub I, conditionally upon the fact that basically they win across all coordinates, in addition to the fact that we're looking at the expectation taken with respect to the probability measure over big X, which is namely the set of questions distributed to the first player, or big Y, namely the set of questions distributed to the second player, or the product of X and Y, which is given by the set of questions distributed to the first and second player simultaneously. And basically what they're doing is what they're doing in this is that they're taking some type of tensor product representation like I described for the viewer and how this is relating to some complexity related theoretic result where their delta factor, which is corresponding to the two-player factor, it's given by 1 over 16 and it's normalized by the anchoring probability to the 5/4 power. And so another result due to Bavarian, Vidic, and Urin for the game player theoretic setting is given by the fact that for the three-player game, they establish a very similar type of result, namely for big O, which is pertaining to complexity related results through big O values of the expected value for games with three participants under alpha anchoring, a generalization of ordinary anchoring. So again, this is just alpha anchoring is just pretty much the type of anchoring that we've always been describing. And namely, they fix questions little x, y, and z from the set of script x from the question from the direct product of the set of script x, script y, and script z, um, and the number of players or in the number of parallel repetitions k, from which there exist unitaries u sub x, v sub y, and w sub e acting on these quantum registers e sub a, e sub b, and e sub c, respectively, such that the expected value of x, y, z of the norm of this tensor product operation of u of x, w sub y, and w sub z times kep psi of anchoring of all the three questions simultaneously minus kep psi of the states with no anchoring is related to that complexity theoretic related result. And the decay of the optimal value provided by Varian, Vidic, and Ewan, that we have been describing from their paper on anchor parallel repetition takes this form. Namely, again, we're looking at little n rounds of parallel repetition, and we're performing anchoring on this game is given by 4 over epsilon for epsilon taken to be sufficiently small, and basically an exponential of minus c times alpha to the 48, epsilon to the 17th, n normalized in s. And s is given by a factor that's a maximum between the logarithm of the product of all the question sets for the players the supremum of that with one. So whichever quantity is bigger, we just take that which is inserted in terms of the denominator of this exponential power. But again, we can just see how similar to a lot of those other types of upper bounds which we have provided earlier in the presentation, there's a lot of striking similarities in terms of the decay or the rate of decay of the optimal value under parallel repetition and how this relates again to some universal constant, which in this case is given by C, the anchoring probability, which is alpha, a sufficiently small parameter, which is given by epsilon, the number of rounds of parallel repetition, which is given by little n, as well as this S term, which is dependent upon the logarithm of the product of questions of the players. And again, this is just to say that we can define the delta multiplayer parameter, which is appearing in the three complexity related results for the multiplayer game theoretic setting, which we have been describing because it's given explicitly by delta multiplayer being by 1 over n, namely 1 over the number of parallel repetitions of this following superposition of logarithms, namely the cardinality of the coordinates, the logarithm of the product of the cardinalities of the questions distributed to each one of the players, as well as plus the log of 1 over the probability of winning across each one of the coordinates. And sorry, or no, that's actually fine. Sorry, I just get sometimes confused with my notation, but yeah, it should be a logarithm of this quantity. And the cardinality of the coordinates, which is expressed in the previous slide, can be identically expressed as a union over the number of such coordinates for each I. And also, furthermore, the natural logarithm of the product of question sets that's related to the delta multiplier threshold is related to this quantity, namely the logarithm of each one of the products of the cardinalities of the question sets, which again, the viewer shouldn't be surprised, is going to come into play in terms of the exponential rate of decay that I'm going to be describing for the multiplayer setting in the next presentation of the series. And this is to say that these types of quantum circuits that we've been describing, they have many similarities between time evolution and quantum circuits for variational quantum algorithms, because in a previous paper, I made use of circuits of this form for approximating solutions to partial differential equations for the Kamasa-Holm PDE. And it's basically relating to the fact that we have countably many input ports, which are serving as just basically they're going to constitute output ports for some quantum nonlinear processing unit CNPU, and how this basically relates to computing a bunch of expected values from the parameters that are given by solutions U to this partial differential equation of interest. So basically, I thought that this type of quantum circuit was helpful and informative to provide as we're closing out this third presentation of the series, because it's really helpful to actually describe how different types of comparisons between quantum information and time evolution can arise between maybe more theoretical quantum information processing tasks and actually quantum algorithms and variational quantum computing. And so this is just to say that all of those systems of expected values and expectations that we have been describing, they're relating to the POVM system. And again, this is just really saying that because we have been describing and motivating several times at different points throughout the first three presentations of this series, that we wanted to establish some type of correspondence between traces of tensor product representations and probabilities, we're just inserting in the place of probabilities positive operator valued measurements corresponding to each player, which will constitute the POVM system, which is again underlying the second complexity related theoretic result. And we're looking at the expected value over coordinates of the norms of each one of these probabilities with the POVMs script POVM1 up to script POVM of big N. And again, this is just related to the fact that I wanted to close out the third presentation of this series by just demonstrating to the viewer that it's always very helpful to consider duality between non-local games, because overall, because our universe is non-local, and that's very paradoxical, but it's one of the main conclusions of quantum mechanics and quantum physics, it's really allowing us to determine whether there are any types of ways in which we can establish, like I've been describing, maybe correspondences or connections between either two-player games or multiplayer game theoretic situations. And this is given by the fact that, like I've been describing for one of my earlier papers on XOR star and FFL games in the two-player setting, I was really able to make a direct connections between XOR and XOR star games because it's relating to basically the following two set of criteria in which pretty much we can establish a correspondence between an XOR game in order to get an XOR star game from an E-bit XOR game in which we're just basically taking the minimum of the cardinality of S and T to be less than or equal to 4 as one condition. And then the second condition that we're describing here is that if we denote little a and little b as two possible measurements for Alice and Bob for some questions little s and little t that are drawn uniformly at random from the referee's probability distribution, if we perform single qubit measurements for each one of these possible questions so that we can determine what are the possible answers that Alice and Bob can provide in response to the questions from the referee's probability distribution, which we respectively denote with big A sub little a sub condition upon S, and also big B sub little b condition upon little t. We can express using the Born's rule the probability of sampling or being able, or the probability that Alice and Bob provide responses little a and little b conditionally upon the questions little s and little t with the Born's rule, which is just basically given by an outer product of the tensor product of these two tensors given by the outer product of the ket psi with Brop psi, which is given by the strategies which they're using to play the game. So this is again just demonstrating how non-locality, which is coming into play in terms of in terms of how these players can actually allow, basically realize optimal quantum strategies using entanglement and other aspects of quantum information can really be established for multiple types or even several types of game theoretic circumstances which could be of interest. And so I wanted to close out with a conclusion in that we further describe anchor parallel repetition. Central to our approach are objects relating to system of expected values, normalization factors, and quantum states corresponding to dependency breaking variables. And this allowed us to establish at the end some very brief comparisons between time evolution of quantum circuits for information processing tasks which appear in variational quantum algorithms. And then the next presentation, the fourth presentation of the series, we'll continue describing how complexity related upper bounds and the three main results are obtained. And thanks for watching.